Good morning. Myself, K. Ravikumar, Associate Professor, Department of Pharmaceutical Chemistry, School of Pharmacy, Nalla Narasimha Reddy Education Society, Group of Institutions. Today, I'm explaining molecular orbital structure of benzene. So when you go to the class, the objectives of this class is, in the end of the class, students able to write or draw the structure, molecular orbital structure of benzene, define bonding and antibonding orbitals, explain the various molecular orbital structures based on stability, explain the concept of HOMO and LUMO. HOMO means highest occupied molecular orbital, and LUMO, lowest unoccupied molecular orbital. So students able to draw molecular orbital structures, explain bonding and antibonding orbitals, explain various structures and concept of HOMO and LUMO. Coming to the molecular orbital structure of benzene, the structure of benzene is a planar. The structure is planar and it is very symmetrical, having hexagonal shape. When it comes to hexagonal shape, the bond between carbon and carbon and carbon, bond length will be similar. The bond length between carbon and carbon will be same. All the carbons in benzene undergoes sp2 hybridization. Carbon-carbon bond, sp2 hybridization, and carbon-carbon bond is formed by the overlapping of sp2 hybridized carbon. So if you see here, this carbon will have a sp2 hybridization. The shape of sp2 hybridized carbon is planar trigonal, and each carbon will try to form three bonds with three different atoms, and it will be having one p orbital, an unfilled p orbital, which will be forming a pi bond with any other atom. So carbon-carbon bond is formed by the overlapping of sp2 hybridized carbon. So if you see this molecular orbital structure here, this carbon and this carbon is having overlapping between these two by sp2 hybridized carbons, and so that it forms a sigma bond because it is a end-to-end overlapping. And when it comes to carbon and hydrogen bond, when you see here carbon and hydrogen, sp2 hybridized carbon is overlapping with s orbital of hydrogen to form a sigma bond. So all the carbons will be overlapping with other carbons and hydrogens to form carbon-carbon bond and carbon-hydrogen sigma bonds. The bond angle between the carbon-carbon-carbon will be 120 degrees angstroms, 120 degrees angstroms, and the bond length between carbon and carbon will be same, that it would be something around 1.39 angstroms. And carbon bond length between carbon and hydrogen will be 1.10 angstroms. You see here, this is the sigma bond formed between the carbon-carbon and carbon-hydrogen, so that the carbon bond length between carbon and carbon will be 120 degrees angstroms. So carbon valency is 4, and it is already formed one bond with hydrogen and two bonds with carbon. There is one unhybridized p orbital which is there on each carbon. So each carbon in benzene will have one p orbital on the planar hexagonal structure, which is not used by for bonding. So these p orbitals are having one electron each, though this one electron in p orbital will be overlapping with another p orbital which is adjacent to each other to form a side-by-side overlapping to form a pi bond. So when there is a overlapping between these two pi bonds, or these two p orbitals, there is a pi bonds form. So when you see here, this carbon and this carbon having p orbital, which is perpendicular to the plane of the structure, are overlapping each other to form a pi bond, and these two carbons are forming a pi bond, and these two carbons are forming a pi bond. To form 3 pi bonds are formed. There is another possibility of forming a bond. So where these two uh, carbons, these two p orbitals may interact with each other. In the first structure, the overlapping is taking place between these two carbons, and in the next structure, the overlapping is taking place between these two p orbitals. So it forms 3 different p orbitals or pi bonds are formed. So overall, there is a delocalization takes place. There is a delocalization of electrons take place from one p orbital to other p orbital to form a ring above the plane and below the plane. So when the pi bond is formed in this fashion, so it forms a benzene structure in this format. And when the pi bond is formed like this, there is a possibility of benzene structure formed like this. Double bonds are in this fashion. And overall structure, if you see the p orbitals which are there perpendicular to the structure of benzene, they overlap each other to form a electron cloud above the plane and below the plane. So carbon undergoes sp2 hybridization and forms sigma bonds with 3 atoms, that is carbon and hydrogen, and have a 120 degrees bond angle because it is a hexagonal structure, and all the bond lengths are same, having a bond length 1.39 angstroms, and the p orbital which is not overlap, which is perpendicular to the plane of the structure, they will overlap each other to form a electron cloud above the plane and below the plane. So in the structure of benzene, we have discussed it is a planar structure, hexagonal, and bond length is between C and C is equal. The pi electrons are delocalized, means the electrons are shifting from one carbon to the other carbon to form a electron cloud. And because of that, there is a amount of energy the system is reduced. That amount of energy which is reduced is nothing but delocalization energy or resonance energy. So the structure of benzene can be shown in a simplified representation like this: hexagonal structure with a ring in this ring in the hexagonal structure that indicates that electrons are moving from one carbon to the other carbon. In other representation, it is a hybrid of two structures where the double bonds are altering each other. So these two are canonical forms. So structure of benzene can be represented in these two hybrid structures, which finally gives rise to this structure. And because of this, electrons are moving from one carbon to other, delocalization takes place. Benzene is having a resistance towards addition reaction. If addition reaction takes place, it would break the delocalization or aromaticity of the ring is broken. So benzene is resistant to addition reaction and oxidation reaction. Rather, it undergoes electrophilic substitution reaction where the benzene is full of electron cloud and it is being attacked by the electrophile. So electrophile is being substituted with hydrogen. That is the reason it undergoes electrophilic substitution reaction. So coming to the bonding and antibonding orbitals, why we need to study this bonding and antibonding orbitals? Because molecular orbitals are formed the overlapping of a combination of two atomic orbitals. So when you come to the benzene structure, it is not only the one structure which is formed in the molecular orbital structure. There are other possibilities, combinations of two different p orbitals are formed to form a molecular orbital. So molecular orbitals are formed as a result of combination of atomic orbitals. So since atomic orbitals are wave functions, they can combine together constructively to form a binding molecular orbital, bonding molecular orbital, and they can be destructively form anti-bonding molecular orbital. What does it mean? If you take an example of atomic orbital, one atomic orbital is having one electron in the outermost orbital, and other atomic orbital is having one electron in the outermost orbital. When they two combine, we'll take example of hydrogen. Hydrogen is having one electron in its outermost orbital, and another hydrogen is having atomic orbital in its outermost orbital. When they do combine each other, there is a formation of molecular orbital. Bonding takes place. So here the bonding takes place because of like phases. So if you see here, the benzene, the atomic orbital which is blue color one phase of 1s orbital will combine with another 1s orbital which is blue color to form a molecular orbital. But when 1s orbital which is having blue color, when it is interacting with or combining with the 1s orbital of red color, which is there is a repulsion between these two phases. So when there is a repulsion between these two phases, there is no formation of bond. Instead, there is a formation of node. What is this node is? Node is a space where there is no electron cloud. Electron cloud is not present here. What does it mean? So when a bonding takes place between two similar phases, the attraction between two atomic orbitals takes place to form molecular orbital, whereas in different phase of orbitals come together, the electrons move away from each other so that there is no sharing of electrons between these two, and molecular orbital is not formed. Instead, it forms a node. Node is a region where electron density is zero. So this is something around molecular orbitals. Means it is not forming a single bond molecular orbital, it is forming two molecular orbitals. One is bonding molecular orbital, another one is anti-bonding molecular orbital. So when you see another example where we combine two p orbitals in end-to-end overlapping, when you see end-to-end overlapping of p orbitals, so these two p orbitals are having similar phases. So white and white phases are interacting with each other to form a molecular orbital. Bonding molecular orbital is taking place. Means when two p orbitals are combining each other in phase, then there is a attraction between these two similar phases. So there is a bonding takes place, and bonding molecular orbital is formed. But when you see here, the electron density is present between the two nucleus, so it is present in the center of the bonding orbital. Whereas if you take the example of out phase molecular orbital, so two atomic orbitals, p orbitals, are having different phases. One is red phase and one is white phase. So when these two different phases are coming together, there is no attraction between these two. So what happens? When they combine each other, there is no attraction between these two, and electrons move away from each other. So there is a formation of nodal plane. When there is a nodal plane formed, so the electron cloud on this region is zero. Such type of molecular orbitals are called as anti-bonding molecular orbitals. So both molecular orbitals are cylindrical symmetry. What does it mean? So when you rotate this molecular orbital in 180 degrees angle, the shape of this molecule orbital will be same. So that means this is symmetrical in cylindrical symmetric in nature. So they are designated as sigma and sigma star. Sigma is designated for bonding orbitals and sigma star is designated for anti-bonding orbitals. So this type of bonding, it takes place in leads to the formation of sigma bonds. So when you see, sigma bonds can be made from s orbitals interactions or p atomic orbitals interactions, provided they form a cylindrical symmetrical molecular orbital structure. So when two p orbitals are overlapping side by side, overlapping, so there is a formation of two different types of overlapping. One is out of phase overlapping and in phase overlapping. When two p orbitals are having different phases, so these two are in different phases. So when they are in different phases, there is no attraction between these two. When they combine each other, they are repelled. They are repelling each other, means electrons are moving away from each other. So there is no formation of bond in side by side overlapping also. So this, it leads to anti-bonding pi star molecular orbital structure, molecular orbital. So this is not cylindrical in nature. When you rotate 180 degrees, so there is the structure is not similar. So it is not cylindrically symmetry. So when you observe in phase overlapping, so here the p orbitals are having same phases, white phase and white, they do attract each other. There is attraction between these two electrons which are there in the p orbital because they are similar phases. So they combine together to form a molecular orbital. When they combine to form a molecular orbital, so it forms a bonding molecular orbital structure. But this is also not having a symmetrical shape, because when you rotate 180 degrees, so the one phase comes to the other phase and then there is no symmetry in position. So these two are not in symmetry. Similarly, we will have some examples for anti-bonding and bonding orbitals. We'll take example of ethylene. When you see ethylene, there are two p orbitals which are present. When these two p orbitals having two electrons, they may interact each other, they may not interact each other, because if they are in same phase, they form a bonding molecular orbital. If they are in out of phase, means when they are in black and white phase, they do not interact with each other. So there is no sharing of electrons here. So that what happens, it forms a anti-bonding electrons, anti-bonding orbital forms. If you see the same example, the two p orbital, pz orbital, atomic orbital having one electron, and this pz orbital is having one electron. When these two electrons are combined together, if they are in same phase, they form a bonding molecular orbital. If they are in two different phases, they form anti-bonding molecular orbital. So there are two different molecular orbitals are formed in ethylene. Similarly, when you see the example of 1,3 butadiene, in the structure we have four p orbitals which are present in each carbon atom. These four p orbitals, they may interact each other to form four different types of molecular orbitals based on the energy. Two molecular orbitals are formed in the bonding molecular orbitals are formed. Two are anti-bonding molecular orbitals. How can you define? One is bonding and one is anti-bonding. That depends on the number of nodes which are formed. If you see in this structure, there is no node formed, but in this structure, there is one node which are repelling each other. In the anti-bonding structures, molecular orbital, there are two nodes are present. In this fourth structure, there are four nodes present. So as the number of nodes increases, the potential energy increases. When the energy increases, the stability of the molecule decreases. So here, when you see the most stable molecular orbital in 1,3 butadiene is first one, and that is we call it as psi1, molecular orbital 1 and molecular orbital 2. They are more stable, and molecular orbital 3 and molecular orbital 4, they are quite unstable. If you see the diabatic structure, see here, there are four p orbitals which are there. In these four p orbitals which are there, the p orbitals are having similar structure, similar colors are present on the same side. So two similar phases are interacting with each other, so that there is a formation of molecular bonding orbital takes place. So this is having a least energy. But when you flip these two, one is having two blue color is present at the bottom and the blue color is present at the top. So this is out phase combination. When there is out phase combination, the bonding is like this. The bonding to these two carbons are forming a pi bond, and these two carbons are forming a bi bond. So this a molecular orbital we call as HOMO. Why it is called HOMO? It is a highest occupied, because electrons are present in this highest occupied molecular orbital. When you come to the third one, the p orbitals are not in similar fashion. The same phases are not in the similar fashion. They are alternatively present. When they are alternatively present, there is a combination. There is a chance of when these two are having similar phases. When these two are having similar phases, there is a chance of formation of bond between these, overlapping between these two, and these two are not overlapping with these two because they are opposite. Because these two are similar, there is a chance of forming bonding. These two are alternate each other, there is no formation of bonding. How many nodes are formed here? Here, there is a node here and there is a node here. So two nodes are present. So this molecular orbital we called as LUMO. What do you mean by LUMO? Is lowest unoccupied. because there are no electrons present in this molecular orbital. It is lowest unoccupied molecular orbital, last molecular orbital, that is having three nodes where each p orbital is not at all interacting with each other to form a bond. So the butadiene has four p orbitals which interact with each other to form four different molecular orbitals. Out of these, first molecular orbital, this is most stable molecular orbital because it is having least energy, and psi 4 is having highest energy molecular orbital, which is unstable. And next second one is called as HOMO, which is highest occupied molecular orbital, and third one we call it as LUMO, it is lowest unoccupied molecular orbital. So butadiene forms four different molecular orbitals. But when you come to the propene system, allyl cation, the possibility of three p orbitals, three p orbitals which are there, there is a probability of forming all the phases on one side and all the phases on alternate side. If all the phases are alternate side p orbitals, they call as anti-bonding molecular orbital. They have there is no interaction between each p orbital, so there is a formation of high energy p orbitals or molecular orbitals are formed. Here, all the p orbitals in the lowest energy bonding orbital, all the p orbitals are interacting with each other to form a molecular orbital. In another molecular orbital, the second carbon p orbital is not interacting either with this p orbital or not this p orbital. It is acting as a free radical. So there is a node formed between these two, so that there is no interaction between these two. Non-bonding molecular orbital have same energy as that of normal p orbitals. So this in this propene system, this molecular orbital is called as HOMO, highest occupied molecular orbital, because it is having electrons in its orbital. This second orbital we called as molecular orbital we called as LUMO. Why it is called LUMO? Because no electrons are available in the molecular orbital, the lowest unoccupied molecular orbital. It is a lowest energy because highest energy orbital is there which do not have electrons, but lowest orbital this is LUMO and this is HOMO. Because when you come to the benzene structure, it is a replicate, it is the double of this propene system. When you come to the benzene structure, finally there are six combinations takes place, because you have six components, six p orbitals are present in the benzene structure. There is a interaction, there is a chance of interaction between these two p orbitals, or there is a chance of overlapping between these two p orbitals. So there is a probability of formation of six molecular orbitals formed. Out of these, the most common stable molecular orbital which is formed is this one we call as psi 1, where the electrons are present. It is the most stable and the least energy, because all the yellow colors, all the orange colors are at the bottom and the blue colors are at the top, means they are overlapping each other to form the molecular orbital structure, which is having electron cloud above the plane and below the plane. This is one. And next one, if you come, three are above the plane and three are below the plane. Means three orbitals, three orbitals are in one phase and three orbitals in other phase. So there is a formation of repulsion between these two. So there is no interaction between these two. There is a overlapping between these three overlapping, and there is overlapping between these three, but there is no interaction between these two. So there is a node formed here. This type of molecular orbital we call as psi 2, and another orbital we have seen, that is in the pi system, there is a node non-bonding orbital which is there. So this will have a in-phase molecular orbital and out-phase molecular orbital. If you see this structure, so this is a non-bonding molecular orbital, and this is non-bonding molecular orbital, and this there is an in-phase interaction, in-phase molecular orbital. So this orange may interact with each other to form a molecular orbital, and this type of molecular orbital we call as pi 3 system. And if it is out phase, there is a pi 5 system where there is a there is no interaction between these two. There is a node formed here. So there is a node formed here and there is node formed here. If you see, there is one node, these two are in the same energy. psi 2 and psi 3 are at the same energy levels because it is having one node. This is one node and this is one node. So there are one nodes here having same energy levels, and these two molecular orbitals are having same energy levels, and these two molecular orbitals are having same energies. Psi 4 and psi 5 are having same molecular orbital, having same energy because they have two nodes, one here and one here. So here also, if you see, these three PR tolls are alternate to each other. Green, that is blue, orange, and blue. Blue, orange, and blue. They're having no interaction between these two and these two, but there is an interaction between these two. So it is forming a molecular orbital, but there is a node formed here. There is a node formed here, and there is a node formed here. So because of that, the energy levels are high, and last orbital, there is no interaction between any of the p orbitals. There is no interaction between this p orbital and this p orbital, this p orbital and this p orbital, because orange and blue there is no interaction, orange and blue there is no interaction. So last, which we called as anti-bonding molecular orbitals. So these three are called as anti-bonding molecular orbitals, which is having high energy, and these three are called as bonding molecular orbitals. Out of these three, this first psi 1 is called as most stable molecular orbital, and 2 and 3 are least stable. And out of anti-bonding orbitals, this is the most unstable molecular orbital, that is psi 6, and psi 4 and psi 5 are least stable. So this psi 4 and psi 5 we called as LUMO, and psi 2 and psi 3 we call as HOMO, highest occupied molecular orbital, because electrons are there in this molecular orbital, highest occupied molecular orbital, and lowest unoccupied molecular orbital, because there is no pi electrons. Electrons are present in the bonding orbital, so it is LUMO. If you see another structure, the 6 isolated p orbitals which are there, they may interact with each other. So when they are interacting with each other, the electron cloud is present above the plane and below the plane. So there is no node, and this is having a least energy. But when you come to the second structures, there is one node, and the interaction between three p orbitals and three p orbitals they are forming, and there is a one node formed. Here also there is a one node form. These two p orbitals, psi 2 and psi 3 are at same energy levels, and these are called as HOMO, highest occupied molecular orbital. And when you come to the next level, the molecular orbitals are having two nodes, so it is divided into two. So they are having highest energy because there is no interaction between green and red, green and red, green and red. So energy of molecular orbital increases. So 4 and 5 are having highest energy. So this type of molecular orbitals we called as LUMO, lowest unoccupied molecular orbital, because no bonding electrons are present. And last one, no p orbital is interacting with any of the p orbital, so it is having more potential energy and least stable. These three are called as anti-bonding molecular orbitals, and these three are called as bonding molecular orbitals. And when you see, you can easily see here, all the p orbitals are overlapping each other. So there is one node here and there is one node here. So these are called as HOMO and these are called as LUMO. This is the most stable molecular orbital, and this is the least stable molecular orbital. When you see all the 6 structures, first psi 1 is the most stable molecular orbital, psi 2 and psi 3 are the second stable molecular orbital called as HOMO, and psi 4 and psi 5 are called as third molecular orbitals, that is LUMO, and 6 is nothing but unstable molecular orbital, the anti-bonding molecular orbital. So this gives different types of molecular orbitals we have discussed, and in the summary what we have discussed is we have seen the molecular orbital structure of benzene, that is most stable molecular orbital structure. We have discussed what is bonding and what is anti-bonding molecular orbitals, and we have seen HOMO, that is highest occupied molecular orbital where the electrons are occupied, and LUMO, that is lowest unoccupied molecular orbital. This is about molecular orbital structure of benzene and different types of energy levels of molecular orbitals. Reference, we have referred Morrison-Boyd organic chemistry by I.L. Finar, organic chemistry by Claydon, organic chemistry by Arenball. And this ends your class. Next class, we will discuss about aromaticity and the different structures of aromatic compounds, whether they are aromatic, non-aromatic, and anti-aromatic. Thank you.